Hello guys, welcome to my channel Learning with Sarita. It's my pleasure in presenting a video on the topic Applications of Gauss law, electric field due to an infinitely long charged wire. In this video, we will discuss the line by line explanation of the topic, related numericals and related one words. First, let us recall the concepts of Coulomb's law and Gauss law. And the Coulomb's law explains the electrostatic force of attraction or repulsion between 2 point charges. Isn't it? I have a source charge, strong source charge here and a unit charge here. What is the force of repulsion? Force of repulsion is given by F is equal to K Q by R square R unit. Now what will be the electric field? F vector by charge, by the unit charge. So E vector will be K Q R unit by R square. Here the Coulomb's law explains the attraction or repulsion between two charges, and the Coulomb's law can be applied to any arbitrary charge configuration. Whatever may be the charge configuration, we can apply Coulomb's law to find the electrostatic force of attraction or repulsion between the two charges. That is, we can find the electric field for any arbitrary charge configuration using the Coulomb's law. Now let's see what's Gauss law. The Gauss law explains the electric flux over any closed surface enclosing the charge. Isn't it? If we have a spherical surface, we can learn how much of electric field lines are coming out of this spherical surface in Gauss law. That is, we can find the electric field using Gauss law if there is a symmetry charge configuration. In Coulomb's law, for any arbitrary charge configuration can be used, but in Gauss law, a symmetry charge configuration is required to find the electric field. And in this topic, we will learn how far the Gauss law is applied to find the electric field due to an linear charge distribution. We consider an infinitely long straight wire. Here, the charges are distributed linearly in uniform manner, isn't it? They are equally spaced and the charges are linearly distributed. Here, when we take a 1 meter length of this wire, some charges will be accumulated, isn't it? And that quantity of charges accumulated in unit length gives the linear charge density. That is, the charges accumulated in unit length gives the density. And the density of charges in 1 unit length is represented by lambda. Okay? That is, for unit length, for 1 meter of length, how much charges is accumulated. If the length increases, the value of the charge accumulation also increases uniformly. And linear charge density lambda is the quantity of charge per unit length at any point on the linear distribution of charges. Since the charges are distributed linearly, the quantity of charges will be uniform. And linear charge density lambda is given by Q by L, that is charge per unit length. Quantity of charges that is accumulated in unit length. And SI unit is given by Coulomb per meter. Coulomb for charge and meter for length. Coulomb meter inverse. And if the charges are positive, then charge density will also be positive. Density is the accumulation of charges. So if the charges are positive, the density will be positive. And if the charges are negative, the charge density will be negative. And now let us learn what type of symmetry is formed in this type of linear distribution of charges. Here is an infinite long wire and we consider a length L in that wire and the charge density lambda will be Q by L. Okay. Now we take a point P at a distance R from the wire. And we have to find the field at this point. We know that electric field is a vector quantity. It has both magnitude and direction. Now let us see the direction of the electric field. Here, for this infinite long wire, the positive charges which are uniformly distributed will be giving out electric field lines in all directions, isn't it? We know that every charge electric field lines will be distributed radially outward in all directions. And here we have a doubt. The charges are uniformly distributed. So the electric field lines tend to intersect. And we know that electric field lines do not intersect. No two electric field lines intersect each other. Then what is happening here? At the point we have to resolve the electric field lines into vertical components and horizontal components. See, for this electric field line, here are the vertical and horizontal component, and for here are the vertical and the horizontal components. And two, we know that the opposite and equal magnitude vectors cancel each other. Direction is opposite and magnitude is same, and so they cancel each other and the resultant will be due to the horizontal components. This is what happening here. All the vertical components gets cancelled and the resultant electric field is only due to the horizontal component. Okay, and you imagine this field will be existing for all the value of radius r around the wire, and we get a circle, isn't it? If for this radius r is taken at any point around the wire, the electric field E, the magnitude of the electric field E will be same. This is for a particular point P. Then what about for all the charges? If for all the charges are considered, then for around the wire there will be a cylindrical Gaussian surface formed. And so the infinite long wire, that is linear charge distribution, is creating an imaginary cylindrical Gaussian surface. Linear charge distribution creates an imaginary cylindrical Gaussian surface. And once a symmetry is formed, we can find the electric flux, that is the number of electric field lines coming out of this imaginary cylindrical Gaussian surface. So next we are going to find the electric flux. We know that the ultimate goal of the Gauss law is to find the electric flux through a Gaussian surface. And here is the cylindrical Gaussian surface which is formed around an infinite long wire where we have considered a length L which is accumulated by charge Q, isn't it? Okay, now for this cylindrical Gaussian surface, the electric field lines will be coming out through the top surface, through the curved surface and through the bottom surface. Now we have to calculate the flux. Okay, that is the number of electric field lines coming out of this cylindrical Gaussian surface. And this cylindrical Gaussian surface has a curved surface and a top surface and a bottom surface. Here the curved surface of the cylinder is parallel to the line charge, and the top plane surface of the cylinder is perpendicular to the line charge, isn't it? The top surface and the line charge are perpendicular, and to the bottom surface and the line charge are also perpendicular to each other. So total electric flux through this closed cylindrical Gaussian surface is given by phi e is equal to closed integral E vector dot dA vector. And this closed integral is for the curved surface, for top surface and for bottom surface. And the expression must be written as integral over curved surface E vector dot dA vector plus integral over top surface E vector dot dA vector plus integral over bottom surface E vector dot dA vector. Now we have to calculate the flux values for each surfaces. First, let us find the flux for the curved surface. Okay, the direction of the electric field is perpendicular to the area element. Here you see I have taken an area element. The electric field lines will be pointing outward radially, and here this area element and the electric field direction are perpendicular to each other. But this area element has a direction A vector, isn't it? And that A vector is perpendicular to the area element. So direction of electric field and direction of area element are both parallel to each other. That is, E vector and A vector are parallel to each other. And the angle theta is 0 between them. Now the expression integral over curved surface E vector dot dA vector is written as integral over curved surface E dA cos theta. And here the angle theta is 0 and the expression becomes E dA cos 0. And here we get integral over curved surface E dA. And we know that electric field E has same magnitude, isn't it? So it is taken out of the integral and written as E integral over curved surface dA. That is, electric flux through curved surface phi E is equal to E integral over curved surface dA. Now let us find the electric flux through the top surface. Here we consider an area element, and the electric field direction and the area element are both parallel, but the direction of the area vector is perpendicular to the area element. So the direction of electric field and direction of area vector are perpendicular to each other. The angle between them is 90 degree. So integral over top surface E vector dot dA vector is equal to integral over top surface E dA cos theta. That is equal to integral over top surface E dA cos 90. And since this takes 0 value, cos 90 is 0, so the flux through the top surface is 0. Electric flux through top surface phi E is equal to 0. Next we have to find the electric flux through the bottom surface. Here the direction of the electric field and the area element are both parallel, and the direction of the area vector is perpendicular to the area element. Therefore the angle between E vector and A vector is 90 degree. That is, E vector and A vector are both perpendicular to each other. That is, integral over bottom surface E vector dot dA vector is equal to integral E dA cos theta. That is equal to integral E dA cos 90 degree. Cos 90 is 0, and therefore the flux through the bottom surface becomes 0. Now we have to add all the flux values. You see, for if the curved surface, the direction of E vector and area element are perpendicular, direction of E vector and direction of A vector are parallel, theta value will be 0. So flux phi E is equal to integral over curved surface E dA cos 0 is equal to E integral over curved surface dA. And for top surface, the direction of E vector and area element are parallel. That is, direction of E vector and direction of A vector are perpendicular. Theta takes the value 90 degree, and integral over top surface EDA cos 90 is equal to 0. And if for the bottom surface, the direction of E vector and area element are parallel, direction of E vector and direction of A vector are perpendicular, and theta takes 90 degree, and the integral over bottom surface EDA cos 90 is equal to 0. And when we substitute all these values, the total electric flux through the closed Gaussian surface will be phi E is equal to E integral over curved surface dA. Here E denotes the magnitude of the electric flux for the curved surface. It is a constant, and that's what we have written it outside the integral. And integral dA represents the total area of the curved surface only. Now we have to find the expressions for E and integral over curved surface dA. Now we are going to find the electric field due to infinitely long charged wire by applying the Gauss law. And by Gauss law we know that phi E is equal to 1 by epsilon naught times Q enclosed. That is 1 by epsilon naught times the charge enclosed. That is E is equal to integral over curved surface dA. That is E integral over curved surface dA is equal to Q enclosed by epsilon naught. So what will be Q enclosed? It is lambda into L. We know that lambda is the linear charge density. And integral over curved surface dA is equal to 2 pi RL. Here you see for the cylinder, the total surface area will be taken as pi r square plus pi r square by 2 pi RL. These two expressions are for the circular bases. Here we are considering only the curved surface, isn't it? So integral over curved surface dA will be 2 pi RL. Now we substitute this for integral over curved surface dA. What we get? E into 2 pi RL is equal to lambda L by epsilon naught. So E will be lambda L by epsilon naught into 1 by 2 pi RL. And here E is the magnitude value. E magnitude is equal to 1 by 2 pi epsilon naught into lambda by R. If we give vector notation, we get magnitude and direction. So E vector is equal to 1 by 2 pi epsilon naught lambda by R unit. Here lambda is the linear charge density and R is the distance from the line charge to the point where the field is to be measured. The electric field due to infinite long charged wire is 1 by 2 pi epsilon naught lambda by R, isn't it? Here what we learn from this expression, the electric field is inversely proportional to R. Here we take the independent variable R in the x-axis and the dependent variable E on the y-axis. As R increases, electric field is decreasing. For lesser value of R, E value increases. And to the electric field is perpendicular direction or unit to the wire. Here you see the electric field E is acting outward, and this R unit is the unit vector, that is the radial unit vector. It is also outward direction. That is, the electric field is along the perpendicular direction or unit to the wire. And the electric field is pointing perpendicularly outward if the charges are positive. So lambda takes the value to be greater than 0. If the charges are positive, accumulation of charges will be positive. So lambda takes a value greater than 0. Then since it is radially outward, we give plus R unit. And if the charges are negative, then lambda takes the value less than 0. And this notation R unit becomes minus R unit since the direction is inward direction. Okay. So far we discussed for an infinite long charged wire. Now let us see whether this expression E equal to 1 by 2 pi epsilon naught lambda by R holds for a finite length of charged wire. That is, now we are considering a wire of particular length L, not infinite, for a particular length L, that is a finite length. Here all the vertical components of the electric field will not be cancelled. Only if the wire is infinite, all the components are getting cancelled. So the electric field value may change here. Okay. So only on the midpoint of the finite length wire, the expression E is equal to 1 by 2 pi epsilon naught lambda by R unit is true. And 2, it is not exactly the same, it's approximately same. So this expression is approximately true for finite length of charged wire, and E equal to 1 by 2 pi epsilon naught into lambda by R holds for a infinite length wire. Okay, here I finish up the theory part here, and next we move on to the numerical session. Here is a numerical. Let me start the timer and let's see how much time it takes to solve this numerical. Okay. An infinite line charge produces a field of 9 into 10 power 9 Newton per coulomb at a distance of 0.02 meter. Here is an infinite line charge. It produces a field of 9 into 10 power 4 Newton per coulomb. It is at a distance of 0.02 meter, that is 0.02 meter, and the linear charge density lambda is to be calculated. We know lambda is in coulomb meter inverse. Here the electric field E is equal to 1 by 2 pi epsilon naught into lambda by R. This expression can be written as 1 by 4 pi epsilon naught into 2 lambda by R. 1 by 4 pi epsilon naught is K into 2 lambda by R. Therefore, E is equal to K into 2 lambda by R. And for E, we know the value to be 9 into 10 power 4. And K 9 into 10 power 9. And 2 into lambda by 2 into 10 power minus 2. Now we have to bring lambda on one side. So what we get? 9 into 10 power 4 into 2 into 10 power minus 2 divided by 9 into 10 power 9 into 2. 2 and 2 get cancelled. 9 and 9 gets cancelled. Here it gets cancelled and becomes minus 5. So lambda is equal to 10 power minus 7. Lambda is equal to 0.1 into 10 power minus 6. Or we can write lambda is equal to 0.1 micro coulomb meter inverse. Okay. It has taken just 2 minutes to solve this problem. Now we move on to the next numerical. Here is a numerical. Let me start the timer. An infinite line charge is at the axis of a cylinder. So we draw a cylinder Gaussian surface and the infinite line charge is on the axis. The length L is equal to 1 meter and the radius is 7 centimeter, that is 7 into 10 power minus 2 meter. And the field at the point is 250 Newton per coulomb. Field at this point is 250 Newton per coulomb. And the flux is to be calculated. Okay. And for a cylinder, the flux is due to the top surface through bottom plus through the curved surface. We know through the top it is 0, to the bottom it is 0, and through the curve the value exists. We have to find flux through the curved surface, and the formula will be E into A. E is equal to 250. So E into, for curved surface, 2 pi RL must be written. So flux phi is equal to E into 2 pi RL, and E value is 250, and then for 2, then for pi 22 by 7, and for radius we get 7 into 10 power minus 2, and for length L 1. Okay, now here 7 and 7 gets cancelled. Here these two, 250 into 2, 500 into 22 into 10 power minus 2. This will be 22 into 5, 110. Then 0, 0 into 10 power minus 2. This will be 110. What will be the unit for electric field E? It will be NC inverse. For radius, meter. For length also meter. So unit will be NC minus M square. Phi unit is N M square C inverse. This is the value of the electric flux through the curved surface. Let me stop the timer. The time it has taken is 2 minutes and 12 seconds. And so you never ever skip the numericals. This one word session, we will find the dimension for epsilon naught. We know that epsilon naught is the permittivity of free space. By Coulomb's law, F is equal to 1 by 4 pi epsilon naught Q1 Q2 by R square. Here epsilon naught can be written as Q1 Q2 by 4 pi F into 1 by R square. That is charge into charge by force into distance square. Now we have to write dimensions for each. For dimension for charge, we can write it as current into time. That is ampere into time. That is written as AT. Q, dimensions for Q is A into T. What is the dimension for force? F is equal to MA, and A can be written as V by T. So MA is equal to MV by T. Again the velocity becomes distance by time. So M into S by T into T. Here for mass we give capital M, for distance capital L, and for time T square here. So MLT power minus 2 is the dimension for the force. And next the dimension for radius, it is L. Now we have to substitute for these AT into AT by MLT power minus 2 into L square. Okay, now we take all the denominator to numerator. M power minus 1, L power minus 1, T square, L power minus 2, then A square, T square. Finally, we get M inverse T power minus 3, A square, T power 4. This is the dimension for epsilon naught. Okay guys, I hope you enjoyed all the sessions of this topic. After watching the video, just click the like button, share my video, subscribe to my channel and travel with me to get full mark easily. Thank you.